We've already laid the foundation that we found our B sub n based on how A sub n behaves for large input values, for large n. And B sub n, we're going to use the harmonic series, and we know that it diverges, and we've already shown the AP reader that. So we're going to put A sub n over B sub n inside this limit, and we're really hoping that we get a real number value out. So let's use some algebra to kind of clean this up a little bit. I get to multiply what's going on in the numerator by n. I'll expand what's going on in the denominator, and I definitely have infinity over infinity. So I have the limit as n approaches infinity, and I'm going to do L'Hopital's rule here. So I have 4n plus 1 over 2n plus 2. Once again, I have infinity over infinity. So another step, another iteration of L'Hopital's leaves me, 4 over 2, that leaves me 2. That is a real number value, C or K or whatever you want to call it. That is an excellent result because this tells me, and therefore I can tell the AP reader, that the unknown function they gave me, the unknown series they gave me, must diverge or diverges by the limit comparison test. So a lot to show for the limit comparison test. I have to show a B sub n. I have to show I know how that B sub n behaves. I have to plop that B sub n in the limit in the numerator with their given unknown series, and then I have to get a result and interpret that result. Since 2 lies between 0 and infinity, that is a result that tells me that A sub n behaves exactly the same as B sub n does, so I know it diverges by the limit comparison test. We'll work a few more examples before we come to class and do some homework problems. So here's an unknown. Our unknown A sub n is 1 over the quantity 2 to the n minus 1. That is A sub n. A sub n is 1 over 2 to the n minus 1. For large input values, the minus 1 on the bottom is of no consequence. It doesn't really affect what's happening for large n. So this turns out to be a really good comparison. Now, what I need to do is I need to state to the AP reader that I know how B sub n behaves. B sub n is a geometric series. This is the work that I would have to show, where R is 1/2, and I recognize the absolute value of R is less than 1. So this series converges. So when I put A sub n in this limit in the numerator and B sub n, that I've already stated converges, in the denominator, I would hope to get either 0 or some real number value. Those are the two results from this limit that are going to be helpful. Since B sub n converges, if I can prove that A sub n is smaller, or that A sub n behaves relatively the same for large input values, then that's going to tell me that A sub n must also converge. However, if I get infinity out of this limit, it's not a good result. So let's plug in our series. We'll clean it up, the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. This is infinity over infinity. And so let's run a step of L'Hopital's. The derivative is the natural log of the base times the exponent. In the bottom, I get the natural log of the base times the exponent. The derivative of minus 1 is 0. This is 1. I have the same thing going on in the numerator that I do in the denominator. That is a super helpful result. This tells me, now notice I go back and I pick up the original unknown series a sub n, and I show the AP reader that this converges by the limit comparison test. I always have to show a test or a type of series that justifies my choice of convergence or divergence. Okay, a few more examples. Here, a sub n is 1 over 2 plus 3 to the n. For large n, it behaves like 1 over 3 to the n. There is b sub n. I'm going to show the AP reader I recognize it is a geometric series where the absolute value of r, which is 1/3, is less than 1, and it converges. Then all I have to do is plop it in the limit. As n approaches infinity, I can go ahead in the first step, and if you can do this, that's fine. In the first step, I can go ahead and do the algebra. This is 1 over 2 plus 3 to the n over 1 over 3 to the n, where I have flipped the bottom and multiplied it straight across. It is infinity over infinity. I can do a step of L'Hopital's. The derivative of 2 is 0. The derivative of 3 to the n is natural log of 3 times 3 to the n. This is 1. And so I would show the AP reader that the original series they gave me converges by the limit comparison test. Now this is where I always get asked, how come I just can't write capital L, capital C, capital T? Because believe it or not, there are other mathematicians that call this something different. And LCT may mean something to one mathematician and something completely different to another. So we're going to write out the name of our test every single time. It looks like a lot of work, but it's really not a lot of work. So here is a sub n. I won't take the time to write it out. We'll immediately go and try to find a b sub n. For large n, we might say that this acts like 1 over the square root of n. And you say, well, wait a minute, there is a 3 in front of it. Yes, there is, but what I'm doing in my head, and it's perfectly fine for me to do that, is I'm realizing, which is what for large n, a is going to act like, I'm realizing that any real number value that's multiplied by a nth term in a series plays no role whatsoever in convergence and divergence. So what I'm doing is I'm getting it out of the way. It's gone. So all I need is this. This is a p series where p equals 1/2, which is less than 1. This series diverges. Now notice, every time, even on b sub n, I'm running a good test, or I'm clearly stating what type of series it is, and using the information from that type of series to say that I know how b sub n behaves. And I need to do all of that before I put it in this limit. So 3 to the n minus 2. Notice some things here. Because if I have a root in the numerator and a root in the denominator, those roots are going to continue to show up, and I'm going to flip and flop and flip and flop and flip and flop. Remember a couple of things algebraically. Roots break up over division. Remember a couple of things from your main limit theorem. The limit of a root is the root of the limit. So I can evaluate that limit inside the root, and that result is going to be the same. That is infinity over infinity. In this case, here we are at the very end of all of our calculus work for Calc 1 and Calc 2. This is one of the very few contexts in which I'm going to let you have a few liberties on not showing every single solitary step in your work. There needs to be an iteration of L'Hopital's here. This is such an easy iteration of L'Hopital's, we can do this in our head. The derivative of n is 1, the derivative of 3 times n is 3. This limit, and the derivative of negative 2 is 0, this limit is going to 1/3. I'm perfectly okay with you going right there. You don't have to show every little single step and minutia in your limits in this context. I am going to qualify that by saying you need to be really careful that you're doing it correctly. If you're not confident in what that limit is doing, show the steps. Do all the meticulous calculus along the way. Make sure your answer is correct. Don't take shortcuts that lead to the wrong answer. But if you're confident in your limit work and you're confident in your L'Hopital's rule, I'm okay with you taking a few liberties here. Now, I'm not okay with you taking the liberties of setting up the original limit. I'm not okay with you taking the liberties of doing bad algebra. But if you want to skip a couple of steps or a couple of iterations of L'Hopital's rule because you're confident what that limit's doing, I'm okay with that. And so in this case, since it's a real number value, not 0, not infinity, I would tell the AP reader that A sub n, the original series they gave me, diverges, I'm comparing it with a divergent P series, diverges by the limit comparison test. All right, we've got just a couple of minutes, but I think we can finish this last example. Here I'm going to find a B sub n that acts like this for large n. This is n to the 1/2 over n squared. If you can't immediately go here and say that you recognize that this is what's going on for large n, then take the steps in between that are necessary. All right? But B sub n, a good B sub n for us, is this series right here. This is a P series where P equals 3/2. That is greater than 1. This P series converges. So I'm going to take the limit as n approaches infinity of n to the 1/2 over n squared plus 1 times n to the 3/2 here in the numerator. Hopefully you can follow the work. I just put this in the denominator and flipped it and multiplied straight across. So this turns out to be the limit as n approaches infinity of n to the 4/2 or n squared over n squared plus 1. This is where I'm okay if you skip a couple of steps, a couple of iterations of L'Hopital's. In our head, we know for large input values, that is of no consequence. And we know algebraically n squared over n squared has a value of 1. Now, if you need to do the 2 iterations of L'Hopital's to get to this result, by all means do them. But in this context, if you're confident in your work and you're consistently correct, I'm going to let you to take some liberties on evaluating the limit. But your result better be right every time. So the original series that they gave you, the square root of n over the quantity n squared plus 1, converges by the limit comparison test. So that concludes this set of videos for this lesson. Come to class next time and we'll let you work some homework problems and you can get more comfortable with the limit comparison test.